कौन है? You started, yeah.
Yeah.
No, Sazzad, maybe you could take over.
Yeah. Good afternoon, everybody. So I'm very happy to introduce Mihir in this lecture series, and this is Mihir's second talk. So I'll request Mihir, please, you can start now.
Yeah, okay. Thanks, Sazzad, for the introduction and also invitation to give a few talks in this lecture series. My voice is clear, I suppose. Is it?
Yeah, it's okay.
Okay. Um, I also want to apologize for again postponing this talk by one day, and I'm great. Yeah, I thank especially Devendra for being considerate. All right. So, so in this talk and the next one, I'm going to give a brief overview of smooth representation theory of p-adic groups. So let me start with some motivation. So roughly speaking, if we start with some new form, cuspidal of some level and some weight, um, one attaches a representation of this group GL2 with entries from adels over Q to this form, and this is so-called the cuspidal automorphic representation. And so this representation splits into infinite part and a finite part. So this infinite part looks like when restricted to, let's say, so this is going to be a representation of GL2 R, and restricted to SL2R, this is a discrete series representation, which some of you might have come across in the last few lectures. And on the finite prime side, these phi p's are representations of GL2 QP, Q completed at P, and this is Q completed at R at infinity. So we want to understand what kind of representations are these as a representation of GL to QP. And so these are so-called smooth admissible representations, and we want to study these in sort of detail in these two talks. Again, this is going to be as I said in the beginning, overview of this representation theory. So I won't be giving all the details. It's not possible, but I will try to give you some feeling or intuition for these kind of objects of a representation of attached to groups like GL to QP. So the first thing is as opposed to GL2R or SL2R, what kind of topological groups GL to QP is. So let's begin with some structure theory for such groups. So let me fix some notation. So F is going to be a non-Archimedean local field of residue characteristic P. So basically F is some finite extension of QP, or F is a field of formal Laura series in T with coefficients from some finite field FQ of characteristic P. Okay. And let this script G be a connected reductive group defined over F. Then we look at the set of rational points of G. So this is a group, and it's going to be a closed subgroup of GL and F. for some n, because it's an algebraic group, linear algebraic group. Now on GLNF, we have a natural topology coming from the topology of F. And again, there were talks on local field, so you know the topology on local field, how it's a non-Archimedean local field. It is it's a locally compact, totally disconnected topology. So the similar topology is it's seen on such groups, and then as a subspace for the we consider this as a so this is going to be a closed subgroup of this group because again the G is defined by some polynomial equations, and it's the embedding of G into GLN is algebraic. So it's going to be a closed subgroup of GLNF, and so whatever the structure we have on GLNF, that's going to be transferred to GO. So let's look at the structure of this group in detail. So as I said, GF is locally profinite group. So in other words, a neighborhood basis of identity of GF is given by compact open subgroups. And there are arbitrarily small compact open subgroups near identity. This is again in contrast with SL2R or GL2R, where you don't have a compact open subgroups. And this is what makes this group totally disconnected as opposed to SL2R, which is connected. So for example, what is such a system of basis of identity can be given by these type of subgroups. So inside GLNF, I have so-called principal compact open subgroups. These are identity. These are all matrices in GLNF, which are identity modulo pi power k, where pi is the uniformizer element. And then you restrict, you intersect this with GF, then you get a system of compact open subgroups of identity for GF. So by definition, so we are interested in p-adic groups, okay, representations of p-adic groups. So that for me, a p-adic group is going to be a closed subgroup of GF for some connected reductive group G over F. So examples like you take F to be QP, then and G to be SON, then SON QP or SP2N FQ double bracket T, or the additive group QP square. This is the degree to unramified extension of QP. This can be considered, this can be seen as a closed subgroup of GL2 QP square as the upper triangular unipotent matrices, the group of upper triangular unipotent matrices and so on. Okay, so so from now on, G is going to be a p-adic group, and again, this locally profinite topology is essentially same as saying that it's a locally compact, totally disconnected topology. So since the group is totally disconnected, G admits a lot of locally constant functions which are not constant. Okay. Again, unlike real groups or complex groups. So let's use this property of p-adic topology to consider a particular type of representations of G. So let pi comma v be a representation of G on a complex vector space such that all the orbit maps from G to V. That means you fix any V and look at it orbit under the G action. So that G is mapping to pi G acting on V. So all these orbit maps are locally constant functions. Let pi comma V be a such representation, and then we call such a representation locally constant or smooth representation of G. So, well, I mean, so what I'm saying is that representation pi comma V is smooth or locally constant. Smooth is maybe not a very good terminology, but it's a very standard one to use for representations of p-adic groups. So pi comma V is a smooth representation if every vector V is fixed by some open subgroup in G. That this is exactly what it means, that the map is locally constant for the orbit of V map. Okay, right. So we know that for p-adic groups, any open subgroup contains a compact open subgroup. So it is equivalent to say that pi comma V is smooth if and only if I consider all compact open subgroups of G and look at the k fixed points of my representation space, then V should be written as the union of all such k fixed vectors of V. Because again, I mean, this just follows from the structure of the p-adic groups. Any open subgroup contains a compact open subgroup. So therefore, V is smooth if V can be written as a increasing union of k fixed k invariant subspace of V over compact open subgroups of G. And another important definition that we call pi comma V smooth representation admissible if each of these k invariant subspace is finite dimensional. Okay. So these are like very basic notions here. So are there any questions? Okay. So let's look at a few examples of smooth representations. So let my group be QP star, GL1 QP, and let me consider a one-dimensional representation of QP star. So that means just a character. So this character is smooth. What does it mean for a character to be smooth? So note that for any if a smooth representation is finite dimensional, then it has to factor through some open subgroup, because suppose V is finite dimensional, then there are finitely many basis vectors and each of them is fixed by some open subgroup. You take their intersection and then you will get a open subgroup. Finite intersection of compact opens is again compact open. So that will fixes the whole of V. So that means the action of G is factoring through some finite open, quotient by some finite open subgroup, right? So here I'm considering one-dimensional representation. So it is going to be smooth if I don't leave chi factors through some open subgroup of QP star. Now, what is the structure of QP star? It is nothing but QP star is P power Z times GP star. So any smooth character actually is determined by its value on P, and a character on ZP star factoring through some finite subgroup. So basically a character of this finite group Z mod p power nz units in that star. So these are basically all smooth characters, complex valued characters of KP star. Now let's look at another example, which is very important actually. So let's consider space of functions on G. So basically representations of a group are the main source is to look at the functions on G, right? And which naturally affords G action. So in this situation, particular what kind of functions we are considering on G. So these are all complex valued functions, locally constant, such that support of F is compact. So support of F is nothing but you take the set on which F does not vanish and take its closure. And then like G acts on this space by right translation here. And so why this function is smooth, this representation of G is smooth. So let's so what does it mean that what does it mean for this representation to be smooth? For any function F here, I want to find a compact open subgroup such that K fixes F, right? So let F be a compactly supported smooth function. So infinity is to denote that we are considering locally constant functions or smooth functions, and C to denote compactly supported. So let F be a smooth compactly supported function. Then support of F is covered by finitely many compact opens, on each of which F is locally constant. This is just unraveling the definition basically. And then the compact open which will fix my F is nothing but the intersection of all these KIs. I suppose this example is clear. So this is a smooth representation and infinite dimensional. And in fact, we will be interested in infinite dimensional representations. So on the first slide, this pi p which occur in automorphic representations, they are infinite dimensional representations. So yeah, so this is an example of a smooth infinite dimensional representation, and I want to let's analyze this space furthermore. So what we have seen is that support of F is covered by some cosets of finitely many these compact opens, which are nothing but cosets of some compact open subgroups. So similar, I can similarly consider finite open cover, but now my compact open is on this side, some Ki prime, and then again take intersection of those. This will tell me that F is actually supported on finitely many K double cosets for some K, which depends on it. So any compactly supported smooth function is actually supported on finitely many K double cosets for some compact open K. Okay, so yeah. So one remark is that this example of the space of smooth compactly supported functions on G is not admissible representation. And why this is so? So let's consider yeah. So in fact the sub representation in which I'm considering functions which are left K invariant, this itself is not admissible for any compact open K. So of course this whole space is not going to be admissible, and why this subspace or sub-representation is not admissible. So by definition, admissibility means that for any compact open K, it's the K fixed vector should be finite dimensional. So in particular, consider this subspace and look at its K fixed vectors. Right, so this is the space. This is going to be the space of K bi-invariant functions, right? Complex valued K bi-invariant functions on G. And this space is not finite dimensional. This actually follows because the set of double cosets of any compact open in subgroup of G is not is in fact countably infinite. The set of double cosets or single cosets, it doesn't matter because we are anyway considering only compact subgroups, compact open. So the set of cosets of K is countably infinite, and that would imply that the set of double cosets is also countably infinite, and therefore the dimension of the space of K by invariant functions is not going to be finite dimensional. And this is countably infinite follows from Cartan decomposition. I suppose this was discussed in the lectures on algebraic groups, but this is basically writing GLNF as disjoint union of. So one can use the Cartan decomposition for GLNF, which has a simpler form than any arbitrary connected reductive group G, and then use that to show that this coset space is not finite. And for the Cartan decomposition for GLNF, looks like that GLNF can be decomposed into a disjoint union of double cosets of GLN ZP, GLN OA for GLN, if F is QP, then GLN ZP, and each double coset is parameterized by non-decreasing sequence of integers, which gives you countably infinite double cosets for of GLN ZP inside GLN QP. Okay, so the fact that this for any compact open subgroup, G mod K is not it's countably infinite. This has a nice, interesting consequences as follows. The first one is the following. So suppose I start with smooth representation, which is irreducible. Okay. Then one can show that the dimension is countable. So it's, yeah. So why this is so? Here, because irreducible is in the usual sense, right? It doesn't have a subspace which is invariant under G action. Okay, so well, V is irreducible representation of G, smooth irreducible. So any non-zero vector is going to generate V. So that means V can be written as a span of pi G of V, as G varies over all group elements. But this is same as span of pi G of V, where G varies over G modulo KV, where KV is some compact open fixing V. Okay, and we know that this, although G can be uncountable, but we know that this quotient is countable. So therefore, V is the spanning space of countably many vectors. So therefore, its dimension is countable. And so one consequence of this is the Schur's lemma, very useful in representation theory, that if I start with some smooth irreducible representation of G, then all maps from V to V, linear maps which commute with the G action, they are basically just the scalars. So In other words, the G endomorphisms of V, the algebra of G endomorphisms of V is just C, isomorphic to C. Okay, so let's quickly take a look at this proof. Okay, so yeah, again, it's very easy. So the thing is, any G equivalent endomorphism of V, G equivalent linear map of V, T, is going to be determined by its value on some non-zero vector, because non-zero vector generates V as a G representation, right? So therefore, the map T mapping to T V is 1 1 from this endomorphism algebra to V, right? And we have seen that V has countable dimension, so G equivalent endomorphisms of V has countable dimension. Okay, now right, so this, but since V is irreducible, this is also division algebra. So if I take any linear operator in this and look at C algebra generated by that linear operator, that's going to be a field. Okay, and so yeah, sorry, I meant to say that any operator T, if you consider the sort of rational, T is invertible because this is a division algebra. So one can talk about rational functions in T with coefficients from C, and this field sits inside this endomorphism algebra. Now, if T was transcendental, then one can check that this function field has uncountable dimension over C. But we know that the endomorphism algebra has countable dimension. So that means T has to be algebraic over C, and C is algebraically closed. That means any map, any endomorphism is actually just the scalar. So here, what are the things that we use in proving this lemma is that C is algebraically closed, and that the endomorphism algebra is countable. So some finiteness condition on the endomorphism algebra. Okay. For example, if endomorphism algebra was just finite dimensional, then also you would get that. Yeah, I mean, instead of saying that its dimension is countable, the endomorphism algebra was just finite dimensional, then also, of course, Schur's lemma will hold. Anyway, so the corollary of this thing is the following: that if it says that smooth irreducible representations yeah, for the G equivalent maps are just the scalar. So in particular, the center of G will act by a scalar. And in particular, if G was abelian, then the irreducible representation must be one-dimensional. So this is something very similar to representation theory of finite groups. Okay, so the remark that I was pointing towards when this is finite dimensional was the following. So so suppose instead of in the Schur's lemma I started with irreducible plus admissible representation, then basically you can check that any this map here for any compact open K, this map would be 1 to 1, and then that would imply that this has a finite dimensional, and that would also give you Schur's lemma, which in fact does not use the does not use the fact that C is uncountable. Irreducibility and admissibility would imply Schur's lemma, which will work over any algebraically closed field, in particular over FP bar. So that's why I've said this is easy. But if I'm just starting with something for something irreducible, then that does not necessarily imply Schur's lemma. I mean over let's say over fields which is not C. So for example, over FP bar, this is not true. Over C, yeah, it is true that irreducibility gives you Schur's lemma. Just now we saw, and over C, it is also true that irreducibility implies admissibility of representations, which is something which is a hard theorem, and maybe in the next talk I will talk about this. Okay. Are there any questions? Okay. Okay, so let me mention a couple of things about admissible representations, maybe. So if my p-adic group is compact, then it is easy to see that any smooth representation is semi-simple. So it's a direct sum of irreducible ones, and irreducible ones are finite dimensional. This is again this is just reflecting the theory of representations of finite groups, essentially. Any over complex number, the representations of finite groups are semi-simple and the irreducible ones are finite dimensional. Further, if the admissibility definition that I gave you on the first slide, it agrees with what you might have seen for the admissible representations of real Lie groups. So this is the second fact here, that if pi comma v is a smooth representation of G and K is some compact open subgroup, then pi is admissible if and only if, when you restrict pi to K, every irreducible representation occurs with finite multiplicity. So this is another way of defining admissibility. It's a equivalent characterization, and again not difficult to prove. Okay, so let's move on to Hecke algebras. So we want to study, the idea is the following, that the representations, one wants to study them as modules over some rings. For example, representations of finite groups, one studies them as modules over group algebras. Here we would like to study smooth representations as modules over some algebra, and that's going to be the Hecke algebra. So right. So let me show you what this algebra is. So let recall that G is locally profinite, in particular it's locally compact group. So there exists a Haar measure on G, unique up to scalars. Left Haar measure, I should say, or left or right. And so one can talk about integrating functions with respect to this Haar measure. So which kind of functions? So again, now we come back to this space of smooth compactly supported functions on G. So note that, recall that this is a smooth representation. So it's going to be union of, it's a union of K fixed vectors of itself, union over compact open subgroups. But this is nothing but compactly supported functions on G mod K by definition. So let f be a function which belongs to some CCG mod K. Okay, any f has to belong to some CCG mod K, because it's the union over all such K's, overall compact open K. So now we can integrate f on G. It's basically a finite sum. So what's that going to be? So if is a compactly supported function on G mod K, right? So K is a compact open. So compactly supported on G mod K means it is actually supported on finitely many cosets of K. Okay. So we just sum the values of f on the coset representatives and multiply that value by the volume of that coset, which is the measure of x times k. So, but since this is a Haar measure, it is left invariant. So xk is nothing but m of k. So so this we can write. So basically, we can integrate f on g, which is nothing but some finite sum over uh, left cosets of k. Is this clear? This is just very okay. Now let me for the next slide assume that G is a group of rational points of some connected reductive group G over a non-Archimedean local field F, and not some closed subgroup, which was my definition for p-adic group. Why? Because connected reductive groups are unimodular. This means that the left Haar measure is same as the right Haar measure, and then one can make this space of compactly supported smooth functions on G into algebra with respect to this product, convolution product. So this is defined to be for any two function f1, f2, f1 star f2 evaluated on G is nothing but this integral, which is again going to be some finite sum similar to what we saw here. You can work this out. So this product makes this space into an associative algebra, and which is what is known as Hecke algebra of G. So this let me say that this doesn't have a unity. It's a ring without unity. It's also not going to be commutative ring because G need not be commutative. So it's a non-unital associative algebra. Okay, so we have this Hecke algebra, and what the point to introduce this as to that was that we want to view smooth representations as modules over this algebra. So so given a smooth representation pi comma v of G, make this into a CC infinity G module as follows. So you take a function and define the action of f on vector v as follows, which we again denote by pi. So pi is going to be some linear operator on v. So pi f is going to be some linear operator on v. Pi f of v is defined to be again you evaluate this function. So at some finitely many coset representatives, and then multiply that scalar by these vectors. So action of those coset representatives on V. Again, this is going to be some finite sum when you fix compact opens fixing F and V. So this makes this smooth representation into a module over this Hecke algebra CC infinity G. And so let us introduce some notation to denote some special elements of the Hecke algebra. So let Ek be a characteristic function on K. So a function supported only on K, and which takes value 1 divided by the measure of k.
Mihir, it seems there is a question in the chat box.
When do we take one-sided cosets and when double cosets? The convolution product will change. No, I don't. Okay, so we are not taking double coset here in the convolution product. So if you look at this definition here, integrating f over whole of g, we are just looking at some compact open fixing f, right? And then looking at cosets of that compact open and summing over those cosets. They are going to be finitely many because f is again compactly supported. So these are just usual cosets, not double cosets.
Thank you.
Okay, you are welcome. So where was I? Yeah. Right. So I'm looking at this function here, which is a characteristic function on k and taking value 1 over the measure of k. So this is supported only on the trivial coset of k right here. Then I just wanted to spell this out for you. So what this operator pi f on v, explicitly this can be written as the following. Again, this is a finite sum. So for f which is right k invariant or fixed by k, compactly supported, pi f of v explicitly is given by this. Maybe I mean this is again very similar to this. One can spell. One can actually spell this out, and then you will get this. So right, the thing is okay, so here what are we doing? Basically we want to define the action of f on v, right? The action of Hecke algebra element or the function on v, and for that we look at the some compact open fixing f that gives me k, and right, and then basically you look at the action of ek on v, where ek is this particular function, and then the action of this x on these vectors. X is a coset representative, and then finally multiply by this scalar fx, and then sum it over all x k's. Okay, so this expression will be useful in proving the next lemma, so we want to now describe the admissibility in terms of the action of Hecke algebra element. So what is this lemma says? Smooth representation pi comma v is admissible if for any f in C infinity G, the corresponding linear operator pi comma f from V to V has a finite rank. Okay, and the thing is, but the definition of admissibility is that all such k fixed vectors of V are finite dimensional. Recall, this was the definition of admissibility, that this is finite dimensional. And then if you take this description of pi f v for granted, then the proof actually follows immediately that pi f is a finite rank operator because the sum is finite and these elements belongs to basically Vk, V's upper K. Okay. So the point of introducing this is the following, that now the lemma allows us to define characters of admissible representations. Even though the representations themselves are not finite dimensional, we can talk about characters. Similar to what you might have seen in for the representations of finite groups, right? So what is this? So you start with some smooth admissible representation, and then uh, attach, okay, and then define a linear map, basically denoted by theta of pi, from CC infinity G to C linear map, basically. So it's a linear functional on this Hecke algebra, which is taking a function f to the trace of pi of f. This makes sense because pi of f has a finite rank. I should have said here image of pi of f. Sorry. Yeah, I forgot to write it as. Okay. So yeah, okay. So this defines a C linear map on this CC infinity G, and I'm saying that this is analogous to characters on G, but this is a non-trivial theorem of Harishchandra that when you are working over extensions of QP and let's say pi is irreducible, well then pi is also admissible. Then actually this linear functional on CC infinity G defined this way by taking trace of functions is that it actually comes from, well, I mean comes from some locally constant function on G. Well, I'm not going to go into the details of this statement, but roughly speaking, it is actually a this sort of linear functional actually comes from some locally constant function on G, and that this function on G is a class function. So now this is just to tell you that the analogy between the representation theory of admissible representations of p-adic groups and representation theory of finite groups, where you define character basically as a class function on G. So this is so this is just some. This is one can find. I mean, the original reference for this is 1978 paper called Admissible Invariant Distributions on Reductive P-adic Groups. So that's why smooth admissible representations play or admissibility is sort of very important finiteness condition, so that you can develop a character theory. Okay. Now I want to. So this is my last slide, and I just want to introduce this another construction, that is the contragredient representation. And so, well, this is some. So when you are given a representation, there are like sort of basic operations to do. One thing is you induce it, restrict it, or take a dual, and so on. So this is the taking dual part. So what is this? So we are given some smooth representation of G, and we first take its algebraic dual, meaning all linear maps, linear maps from V to C. So home V to C, but this thing equipped with the usual G action need not be smooth. So that's why one takes the smooth vectors in the algebraic dual. What does this mean? It just means that you basically take a union over all k fixed vectors of this home space as k varies over compact open. So so this space we denote by v tilde, and it's called the contragredient representation of v. It's the another word is smooth dual. So it's the algebraic dual, and then take consider all smooth vectors, or yeah, all vectors which are fixed under some compact open. That's the thing. So the contragredient operation is important because it preserves admissibility, it preserves irreducibility, and when you apply it twice, you get the original representation back. So it's contragradient basically gives you auto equivalence of the category of smooth admissible representation. Okay, so the this why it preserves admissibility is very easy to see because what we want to show is that k fixed part of this v tilde contragradient is finite dimensional, right? So I claim that this is in fact sitting inside the linear dual of v upper k, and this is because the following. So start with something in v tilde upper k, lambda. Lambda is a linear functional, right? And write v, the restriction of v as v upper k direct sum w. So recall that compact open subgroups. For compact open subgroup, the smooth representations are semi-simple. So when I restrict v to k compact open, it's going to be some direct sum of k representations. So I'm taking the trivial part out, and the non-trivial part is w here, non-trivial k representation. Now take the restrict this linear form lambda to w. You will see just some simple check will show you that it is in fact k equivalent map from w to c, where k is acting on c as a trivial representation. But this space is zero because w doesn't contain any non-trivial k representation. All k trivial part is here. So this lambda restricted to w is zero. So that means that lambda, this linear form, is actually a linear form on v upper k. So that means lambda belongs to home v k to c. So we have showed that v tilde upper k is a subset of home v k to c, and we know that this is finite dimensional because v is admissible, so v upper k is finite dimensional by definition. So this is just some easy proof that contragradient operation preserves admissibility. These are, I'm not showing the argument for this. Just one remark I want to end here with is the following, that why do we consider smooth vectors in the algebraic dual and not just algebraic dual, or in the other words, why the algebraic dual of smooth representation need not be smooth? Well, because you see, the smooth admissible infinite dimensional representation have countable dimension because they are sort of increasing union of finite dimensional spaces, and the union is over countable set, countable index set. So smooth admissible infinite dimensional representations have countably infinite dimensional. So if I just take algebraic dual, that's going to have uncountable dimension. And then so it cannot be smooth because in this proposition we have seen that if it was smooth, then it would have again be admissible, and then it would have countable dimension. So that's the thing, just some uncountable, that basically the algebraic dual of countable is uncountable. That's why we don't get smooth representation when we just take algebraic dual. Okay, so that's all I wanted to tell you in this lecture. I finished a few minutes early. Yeah, the next talk we will explore smooth representations further by discussing some standard constructions like compact induction, parabolic induction, and I will talk about some classification of smooth irreducible representations. There we will see the notion of supercuspidal representation, which are sort of building blocks of all smooth irreducible representations. Okay, yeah, I stop here.
Let's thanks Mihir for the nice talk. So are there any questions? From the audience, are there any questions? Mihir, could you show your first slide of this
Yeah.
talk?
Yes.
Yeah, what was your motivation here then, considering F as a cuspidal eigenform in this talk? The correspondence you have shown here, it is for only for GL2 over Q, no?
Yeah.
So you
Yeah.
wanted to make some comment regarding this correspondence, or?
Or I did not. So correspondence as in no. I was just saying that when you start with some cusp
This is
eigenform.
for the global representation, no?
Right. Yeah. So the thing is, there is a correspondence between cuspidal automorphic representations of GL2 over Q and new forms.
Yeah, that is my.
Yeah.
Okay.
And the correspondence one side is given by you take some new form and consider the GL2 AQ representation generated by the corresponding automorphic form. So if gives you some automorphic form, and then you look at the representation generated by uh, that automorphic form that gives you reducible representation of GL2 cuspidal
Okay.
automorph.
Yes. Thank you.
Yeah.
Are there any more question? If there is no more question, let's thanks me for the nice talk.
Okay. Yeah.
Okay.
You're welcome.
Okay, mate, then see you in the next talk.